forgot to record. All right. I already said it all to the class, but I wasn't recording. So just read this. If you're just coming in, just read this. And I just did that. I just checked out of the meeting, didn't I? My goodness, I'm having a heck of a time. There we go. Got it. All right. So just anyway, so we're going to talk about hypothesis testing tonight, and then Thursday we'll do the math. You guys got this. We're almost done. This week is the last of the new material, and I will have a Zoom meeting on Tuesday next week for before the test, so that we can do like office hours. That office hours seems to be pretty helpful. So we will do that again on Tuesday. And then Tuesday next week will be our last Zoom meeting, because after that you have your test and you have your final project, and that's it. And then we're done. So we got this. Oh, also something you all should know. The quiz number 7 is extra credit. So I will not be putting that in the emails. Basically, it is privileged information for those who watch the Zoom videos or show up to Zoom, but it is extra credit. So it is your choice whether or not you want to do it. I highly recommend, unless you are one of those with a high A in the class, just do it. So, but it won't hurt you. So there you go. So some of you have asked me, hey, is there a little bit of extra credit? That's where it is. So the quiz number 7 is extra credit. All right, moving on. So you've all heard the words hypothesis before. So we make a hypothesis about a characteristic of one or more populations. So we're going to be working on a single population parameter. So looking at like a proportion of something, or like the average something, we're going to be making a hypothesis about that. And then we will test that hypothesis and determine whether or not it is likely to be true, or whether we can reject it. And so that is what we are doing here tonight. Well, Thursday we'll do the math, but we're going to learn about that tonight. So here are some examples regarding claims, and we're going to be revisiting these frequently. So in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So 62% is the data that we already had, and a researcher thinks it's different. So they're going to gather data, and they're going to try to prove that it is different than the 62%. This would be a hypothesis. Here's another one. According to a study published in March 2006, the mean length of a phone call on a cellular telephone was 3.25 minutes. A researcher believes the mean length of a call has increased since then. So the last time, the first one said that they think it's different. So they didn't say greater or less than. This one, the researcher believes that the calls are longer now. So previously they had data that showed it was 3.25 minutes. Now they're going to collect data to try to show that it is increased since then. Lastly, using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With our new equipment, the quality control manager believes the standard deviation has decreased. So they had their standard deviation, and now they have new equipment. So they're going to try to show that the standard deviation is better now and try to change that. So these are 3 different ways that they can make a hypothesis. So there's no math here yet. You don't have to use any of your tools yet. These are just showing you statements of hypotheses. All right. So we test these with sample data because we can't get the entire population. If we had the population data available, there's no need to make a hypothesis, because we were able to ask everybody in that population. So we are going to be using sample data. So that's all that is about. All right. So what we do is a hypothesis testing. So we take sample evidence and probability to test the statements regarding a characteristic. So basically what we're going to do is we're going to determine, like we're going to take a sample, and based on the information we originally had, so the original proportion they gave us, or the mean or whatever, we're going to determine if the sample that we got, if it's likely to happen based on the original evidence. So don't worry about memorizing that, but that's basically what's happening. So that's a really ugly normal curve, less percent 10, that's perfect. So if I had a mean here that they gave me, this is the mean that they gave me. And what I'm going to do is I'm going to build a confidence interval, because we've done that before. We're going to build a confidence interval, and I'm going to take a sample. And I'm going to take a sample and determine whether or not my sample, like my sample mean, lands in here or lands out here. And that's going to help me determine whether my hypothesis is true. If my sample that I took, the data that I found, and lands outside my confidence interval, we're going to say that the original mean probably isn't true. But if it lands inside, then we're going to say, yeah, we don't have enough evidence to say it's not true. That's basically what we're doing here. Don't worry, you don't have to do any math with it yet. I'm just kind of giving you an overview. So if it's confusing, don't worry, we're going to math it out later. All right, here's our steps. The first step, make a statement. I don't know why this is slow of getting there. First thing you're going to do is make a statement. So you're going to say 52%, like it is said that 52% of all people drive alone to work every day. I'm making stuff up here. So that would be my statement. And then I would say, I believe that percent is greater today. So you have to make it a statement like these ones that we did back here. So I could use this one right here. I'm saying, I think it's less now than it was before. I don't know why it's taking so long to go back to the other screen. So you make a statement like this. I am saying, I think it's less. I haven't collected any data yet. Go back over here. Uh-oh, come on, hurry up. You can do it. You can do it. Okay. So then you collect your evidence. After you've made your statement, you've made your hypothesis, you're saying, I think that that's not true anymore. Then you collect your evidence. So now I'm going to collect the evidence in order to test the statement. Next, I'm going to analyze the data to assess the plausibility of the statement. So I'm going to find out, what is the probability that I got the information I did in my sample data if the data that you gave me originally was true? If that original mean is the mean, what is the probability that I got the sample that I did? So that's what we're going to do. And then you make some conclusion. You use big flowery words, but you guys don't have to use super flowery words. I don't require that. All right. So this is where you need to start actually writing stuff down. So a null hypothesis, it's the symbol is H sub 0, H naught is how you would say it. This is the statement to be tested. So with the null hypothesis, we are going to assume it is true until we've shown something different. If we have evidence it's not true, then we will reject it. But we are assuming the null hypothesis is true until we've shown otherwise. This H naught right here, H sub 0 is how you write that. Null hypothesis, or H naught. My high school students call it the hoe. It's okay. If that's what it takes to remember it, then go for it. Then the alternative hypothesis. This is H sub 1. You occasionally will also see it as H sub A. I don't think that my open math does that, but you'll see it both ways. This is what we're trying to find evidence to support. We're trying to say, like, if I think the standard deviation is less today, then my null or alternative hypothesis would be that we think the mean is less than whatever the value they gave. We are trying to find evidence to support this, and we are going to math it out. Not today, Thursday. So this is what it's going to look like. So if we are saying, like that very first question, when we say something is not equal, if it says something like not equal or if it says different, if it says the word different, it doesn't say less than or equal to or greater than, doesn't say less than or greater than, it says different. This is what it's going to look like. My H naught would be that whatever parameter we're looking at equals some value. And then the null hypothesis would be that that parameter does not equal some value. This is a two-tailed test. This would be a two-tailed test. If it says different or not equal, it's a two-tailed test. So what this means is I'm going to have a positive and a negative z-scores. These are going to be a negative z and a positive z. And I'm going to be looking at, does my sample land me in one of these two tails? Because if it does, then I'm going to reject my null hypothesis. This is a two-tailed test. Next, a left-tailed test. So once again, the null hypothesis is always going to look the same. Some parameter equals some value. But the left tail is that the parameter is less than some value. You will see the word less than for a left-tailed test. What that looks like, once again, I'm going to draw a picture because I can. So that's going to look like is I'm going to have one z-score, and it's going to be a negative z-score right down here, negative z, and I'm looking for, does my sample land me outside of that z-score, lower than that z-score? That's what I'm looking for. This is a left-tailed test. We'd have one negative z-score. I bet if you really thought about it, you could figure out what a right-tailed test was. Right-tailed is greater than. So my null hypothesis always looks the same, but my alternative hypothesis would be that the parameter is greater than some value. So it would look like this. If I draw a picture, I'm going to have only a positive z-score up here somewhere. And I am looking for, does my parameter or does my sample land me above that z-score? So there we go. There's our three types of tests. Give you a moment to draw some pretty pictures. All right. In other words, the null hypothesis is status quo or no difference. It always contains a statement of equality. We assume that the null hypothesis is true unless we have evidence to say it is not. We are looking for evidence to support the alternative hypothesis. We're trying to find evidence to show that the alternative hypothesis is true. But until that case, it's kind of like an innocent until proven guilty thing. We're believing the null hypothesis is true until we prove it is not true. I'm going to write the innocent until proven guilty because it's a really kind of great way to remember it. There we go. And then my Y is really ugly. There we go. Questions so far? All right, moving on then. Okay, so we're going to write our null hypotheses and our alternative hypotheses, and we're going to talk about whether they're two-tailed, left-tailed, or right-tailed. All right, so A, in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that percentage is different today. So different means two-tailed test. Is it right there? Yeah. Different means two-tailed test. It's going to be on the next screen, but for some reason, writing it down and talking it through seems to be helpful. So this right here, this right here means it's two-tailed test. Our null hypothesis always has an equal. So our H sub 0, it looks like this with a colon. So this is a percentage. So our P equals 0.62. We always write them as a decimal. So my null hypothesis is that the proportion of American adults who regularly volunteer is equal to 0.62. That's my null hypothesis, always equal. It's always equal, always equal. Because we are believing this is true until we find evidence to the contrary. My alternative hypothesis, that's a 1, is that P does not equal 0.62. So a two-tailed test will always have a not equal. So this number doesn't change. This number right here, this number doesn't change. The only thing that changes is the symbol. Changes from equal sign to not equal sign. The numbers do not change. Questions? Okay, let us real quick here. So this is just exactly what I just said, just with a lot more words. A lot more words. Has the null hypothesis right here and the alternative hypothesis right there. All right. Let's go to the next one. According to a study published in March 2006, the mean length of a phone call was 3.25 minutes. A researcher believes the mean length has increased since then. So it thinks it's greater than. At least this is different than the skew. Remember, the skew was like opposite of what you think. This is exactly what you think. Greater than goes to the right because bigger. Bigger is to the right on the number line. So this is a right-tailed test. Because to the right is where greater than is. So my null hypothesis, we're looking at the mean. So we think the mu equals 3.25. It is okay if you write the word minutes. It's not necessary. It doesn't matter. I don't think my open math has minutes. Units are not necessarily important here. It's really up to you. My alternative hypothesis, once again, the numbers and symbol, the number and mu don't change. The only thing that changes is the greater than. The equal sign goes to greater than. Still alive? We're doing okay? 10.1, I believe 10.1 is its own assignment. I can't remember. But 10.1 is all this stuff is determining what the hypotheses are. Can't remember if they're separate. Might have to go look. Let's see. I'm going to go to my open math right now and check.
It was separate.
Okay. Yep. Thank you. Yeah. So 10.1 is basically all like talking about like null hypotheses and things like that. I believe it might do. Oh, I'm having issues now on my other computer. Open up. Okay. Well, shoot. I can't make it go. Can't make it go full screen now. It's not letting me. Come on, full screen, side by side mode. No. Okay, forget it. My other computer's being rude to me. All right. So this is all exactly the stuff I just said. We have the alternative hypothesis with the right-tailed test. And then my null hypothesis is right there. Fit to window, 100%. Oh, shoot. I don't want that. Okay. There we go. All right, now we're good. Okay, next one. Using an old manufacturing process, the standard deviation in the amount of wine put in a bottle was 0.23 ounces. With the new equipment, the quality control manager believes the standard deviation has decreased. So once again, our null hypothesis always has an equal sign. Oh wait, first, it is decreased, so that means less than. If it is decreased, it's less than, and less than is left on the number line, so this is a left-tailed test. So I'm gonna have to find a spot to write my null hypothesis. So the null hypothesis, H naught, sigma equals 0.23. So it's always equals. And then my null hypothesis, the only thing that changes is the symbol between the sigma and the 0.23, and it is less than, because decreased would mean less than. Questions? All right, and this just exactly what I just said. I just feel that me talking you through it sometimes is better than giving you a wall of words. Okay. So here are the different outcomes of the hypothesis testing. And I had kind of a revelation about this talking with another stats teacher. So I'm going to try to, I don't know, I'm going to try to hopefully get this better understanding. So we can reject the null hypothesis if we can prove, or if we have evidence that the alternative hypothesis is true, we reject the null. So if we have evidence that the null hypothesis probably isn't true, we reject it. Or you can do not reject the null or fail to reject. If we don't have evidence to show that the alternative hypothesis is true, then we fail to reject. We don't ever accept the null. We would just fail to reject it. It's kind of like proving somebody, we say somebody's not guilty. We don't call them innocent. They're just not guilty. So we're just failing to reject. Okay. So long time ago, back last chapter, we talked about alpha. So remember, if we had a 95% confidence interval, our alpha was 0.05. It's just the difference between the 95% and 100. So this right here is the not the confidence interval. It's the outside, the percent that's outside of the confidence interval. This right here is the probability of erroneously, I love that word, erroneously rejecting the null. So this is also the probability of making a type 1 error. So the probability of making a type 1 error is this right here. And a type 1 error is just you rejecting the null when you shouldn't have. So let's say that I found that, so remember they thought the mean phone call was longer than 3.25. So let's say that I figured out the mean length of a phone call is actually 3 minutes. That's not longer than 3.25, but I decide to reject the null. So I erroneously rejected the null. So that's a type 1 error. I do not grade harshly on type 1 and type 2 errors because it's something that's hard for me to wrap my brain around sometimes until this recent revelation anyway. I grade really lenient on type 1 and type 2 error stuff, super lenient on that. So just letting you know, put something in there and at least attempt to give me your reasoning, but I am going to be super lenient on that. So the type 2 error is just the opposite. So if my alternative hypothesis is true, yet I don't reject the null, this is a type 2 error, and this is beta. So my beta is, I don't even have a value for that, but the beta, and as the alpha gets bigger, the beta gets smaller. If the beta gets bigger, the alpha gets smaller. I'm not really concerned about this. If you don't mention beta or alpha at all, I'm not going to get mad at you, but just do your best. And if you just do your best, I'll give you credit for it. If you just attempt to explain, I'll just give you credit for it. So type 2 error or beta is not rejecting the null when you should. Type 1 error is rejecting the null when you shouldn't. So as I said, just do your best on these and I will go easy on you. It's something that I have that is, I believe it's on the chapter 7 quiz. Just do your best. I believe I have 1 question on the test. Just do your best and you'll get full credit for it. Don't leave it blank. You got to put something in there and try something, and I'll give you full credit. All right. So let's talk about what these errors would look like. So 2008, 62% of American adults regularly volunteered for charity work. A researcher believes that this percent is different today. So a type 1 error would be, so it's, remember, it's rejecting when you shouldn't. So if I calculated, if I took a sample and 62% of that sample volunteered their time regularly for charity work, but I said that the null was rejected, then that would be a type 1 error. I think I have it right here. So if I conclude that the probability is not 62, but it actually is, then that's type 1 error. Type 2 error is if I find out it is different, but I don't reject the null, then it would be a type 2 error. Okay. According to a study published in March 2006, the mean length of a phone call was 3.25 minutes. A researcher believes it has increased since then. So a type 1 error would be that I rejected the null and I stated the mean length of a phone call is greater than 3.25, but in actuality, it is not greater than 3.25. Type 2 error is if I find out that the mean length of a phone call is greater than 3.25, but I don't reject the null. If this is confusing, it's okay. Remember, just try something and you'll get credit for it. And then here's a really great rule of thumb right here. Type 1 error, rejecting ho when ho is actually true. Type 2 error, not rejecting it when the alternative is true. This right here is your cheat sheet. If you just keep this in your notes, you should be good. All right. Questions? Okay. I'd already said this. So what the probability of making a type 1 error at the alpha is chosen before. We call this the level of significance. Alpha is the level of significance. So we choose that probability of making the type 1 error. This level of significance, just like with making our confidence intervals, it tells us where our boundaries are. It tells us what percent of a probability is okay. You'll see that Thursday. So we will be using level of significance. So remember we used the critical values before. We are still going to use critical values, but we're going to base it on this level of significance, this alpha. It really is not as complicated as it sounds. And I already said this also, as a type 1 error increases, type 2 error decreases and vice versa. Don't even worry about that. All right. Let's actually get into some nitty gritty here. I already said this. We never accept the null. We just fail to reject. You say we do not reject, or you say fail to reject. I say a lot of things that are on future slides. Sometimes it just fits in the conversation earlier. Okay. Okay. So for the conclusions, there's a whole lot of words. Their conclusions are super, super wordy. They have really, really wordy conclusions. So, I mean, you want the basics of what these conclusions are. I will be asking you definitely on the test, I will be asking you to write out a conclusion. So you do not need to be as wordy as these. So our sample evidence indicated that the null hypothesis should be rejected. So we're going to show the wording of that conclusion. So the statement in the alternative hypothesis is that the mean call length is greater than 3.25 minutes. Since the null hypothesis is rejected, there is sufficient evidence to conclude the mean length of a phone call is greater than 3.25 minutes. That's a whole lot of words. I probably would just say, I would probably start here. And I would say, therefore, we reject the null hypothesis. That would probably be my statement, starting here and then ending here. Because that's just it. Because I stated my null hypothesis like earlier in the process, I don't feel it necessary to reiterate it again in my conclusion, if that makes sense. Right. Next one. Suppose the sample evidence indicates that the null hypothesis should not be rejected. Here's the results here. Since the null hypothesis is not rejected, there's insufficient evidence to conclude the mean length of a phone call is greater than 3.25 minutes. So I probably would start right here. I would say there is insufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25 minutes. And I would not say this. I would not say this. I would say, therefore, we fail to reject the null hypothesis. So this stuff right here, I say, let's see here. And then I would write that. So if altogether it says there's insufficient evidence to conclude that the mean length of a phone call is greater than 3.25 minutes. Therefore, we fail to reject the null hypothesis. To me, that's just better. I mean, if you want to write all this other stuff, go for it. But it just seems like a whole lot of extra words to me. As I've said before, textbook writers, I think they get paid by the word. I'm going to erase all this now. But this is just a lot. All right. We are now in 10.2. If you keep track of that kind of thing, we're now in 10.2. So 10.1 is all just about setting it up, basically, nothing about actual math. So 10.2 talks about how we test the hypothesis, how we know whether or not we reject our null hypothesis. It doesn't do any of the math yet, but it shows you how we determine whether or not we fail to reject or whether or not we reject. So a researcher obtained a random sample of 1,000 people and finds that 534 are in favor of banning our cell phone use while driving. This would be our p-hat. So the p-hat is basically 53.4%. So does this suggest that 50%, that more than 50% of people favor the policy? Or is it possible that the true proportion is less than 50%? We just happened to survey a majority in favor of the policy. So would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5? How do we determine that something is convincing or statistically significant? So way back when, we talked about what an unusual value is. Y'all remember that? Back when things were easier? Remember before we said anything less than 5% is considered unusual? So here, we're still kind of doing that, but instead we're going to be talking about whatever our alpha is, anything less than whatever the percent is that our alpha is would be considered unusual. So if my alpha is 0.025, then anything smaller than 0.025 in this case would be considered unusual. So we just look at our alpha to determine where unusual is. Don't worry, I have a good screen that's going to help you there. There's another way that we can test this, and let me talk about that. So if something is statistically significant, we would observe results that are unlikely. So as I said, if it's less than whatever our alpha is, it is unlikely. Therefore, it is statistically significant. I'm not going to require you to use the words statistically significant, but the words are there and it is vocabulary. So there you go. So let's move on. So to determine if it is statistically significant, we will build our probability model. We still look at this. This doesn't go away. We need to make sure that our sample size is big enough and it is sufficiently small. We're going to make sure it's less than 10% of the population or 5% of the population, as we've been doing. And we're going to be looking at our p hat is going to become our mu. So we will find our standard deviation. We're going to find all of that crazy stuff. Don't worry, this is not new formulas yet. We're not mathing today, so you don't need to math this out. So I have a confidence interval here. My confidence interval goes to these two values right here. All I did was build a confidence interval. So anything in here, if my sample lands me somewhere in here, I would fail to reject. If my sample lands me out here or out here, wait, are we looking for greater than? Oh, we're looking for just greater than, right? Higher than. So we're looking, sorry. If it lands out here, I would reject. That's basically all we're doing here is we're looking at the confidence interval and we're determining, we're looking at whether or not our sample lies within that confidence interval. But our sample was over out here somewhere, right? So therefore, we would have to reject our null because our sample puts us out here in this tail. Does that make sense? Okay. So there's two different ways that we can look at it. Here's the classical approach. If the sample proportion is too many standard deviations away from our mean or our proportion that we gave, our assumed population proportion, then we would reject. So whatever that ends up being, so you were looking at them with our z-scores from the critical values, and it was like 1.96 or 2.575 or whatever is chosen based on our alpha. If we are more standard deviations away from the mean, our sample is, the z-score, like let's say that my alpha, that the z-score for my alpha gave me 1.96. And then the z-score for my sample was 2.05. Then we would have to reject. Because this one right here is more standard deviations away than this is. So that's how we would learn to reject. If that makes any sense. So this is this approach right here. And I think that we're going to get more into it here. Yeah, so see, we are 2.15 standard deviations away from the mean here. Because this is too many standard deviations away from the mean, we would reject the null. When we do some examples, it's going to help. We'll be doing examples on Thursday. It's really going to help with this. So I think back here, this was 2 standard deviations plus 2, and this was minus 2 standard deviations. So 2.15, a z-score of 2.15 would be out there somewhere. My drawing's really ugly. Equals. All right. Let's look. Whoops, I went too far. Okay. This is a lovely picture. Look, this is better than my picture. So the area, I just looked at we have the area under the curve of a z-score of 2. Because we were more than 2 standard deviations away from the mean. All right. So if our null hypothesis were true, then 97.72 of samples would be less than our sample. Woo! Oh, sorry. Because of the area under the curve. So I'm going to move on because I think that this is just going to confuse you more. So take a look. Let's talk about the classical approach. So I used to really, really like the original approach with the z-scores. I am now starting to lean more towards the classical approach. You guys are not going to have a whole lot of choice on this. You will have a choice on this on your test, but pretty much my open math will tell you which one it wants you to use based on what it asks you for. So you'll have a chance to develop which one you like best, but on your test, I'm going to let you choose. So because I really feel like we should be able to choose which math method we like best. So let's take a look here. So our p-value approach. So what we do is, this is a whole lot of words. We determine what is the probability of getting 0.534 for a sample proportion if our population proportion is 0.5. So we basically would just determine the probability of getting that. If that is smaller than our alpha, then we would reject. So for example, I take a look at what the probability of getting 0.534 is. If that probability lands me in my tail, with this being the alpha spot, then I reject the null. So let's say my alpha, I don't know what alpha is here, but let's say alpha is 0.05. And I have that the probability of getting p hat greater than, I'm making up numbers here, 0.534. Let's say that that was 0.027, which I think might be close. So if I get that probability is that small, since this number is smaller than this number, we would have to reject the null hypothesis. Because this probability is smaller than my alpha, I reject. As my high school students like to say, if the p is low, reject the hoe. Yes, they say that. I know, but it works. It sticks in your brain and it makes sense. High school. It's high school. The p is low, reject the hoe. Yeah, it's high school. All right. So we found the probability. So we found that the probability of getting greater than 0.534 is 0.158. That is smaller than 0.05. My alpha, 0.05. This number is smaller, therefore we reject it. That probability is smaller than my alpha, so we reject the null hypothesis. Questions? Right, I have one more slide. This is it. The probability of getting a sample proportion as extreme or more extreme than the one obtains is small. Therefore, we would reject reject the null hypothesis. So we have not finished 10.2. So you won't be able to do 10.2 homework yet. You should be able to do 10.1. I am stopping here before we get to the math. And I'm really going to reinforce it on Thursday. And then at the end of it, I'm going to give you a nice pretty slide that compares the two. So you'll be able to see, okay, if it asks for this, use this formula. If asks for this, use this formula. It's going to be really, really well laid out. And I believe that you guys already have that handout, but I will lay that out on Thursday. So that should be a really good cheat sheet for you. And also another thing, so I'm going to show you before we get to questions, Q&As that you asked me for. If you go to the stuff in, why does this do this? It's so rude. So if you go to the assignments and lessons, I just don't understand why it won't let me. There we go. Okay. So if you go down to the heck, the week 10 stuff. I don't know if you've all looked in the week 10 stuff yet. If you look in the week 10 stuff, there's a really great, I say great because I made it and I like it. There's this final review PowerPoint right here. Let me show you this. If it'll open up for me. Sometimes things happen weird for me when I'm on Zoom. Let's see, come on, open. It's thinking about it. Come on. Okay, it says it's opening it. Let's see if I believe it. Come on. I don't see you. Okay, maybe there we go. All right. So this might even help you with what you're doing right now. So you have the confidence interval page right here. It shows you so this is when we are estimating mu, and it shows what point estimate is, it shows you the margin of error, shows you your confidence interval, what the critical value is, how to find n, round up to the nearest whole number, and the calculator function you use. This one over here shows confidence intervals to estimate p-hat or proportion, and it shows you all of the different things to use. And it all keeps it in one nice, pretty package here. One thing I'm going to add to this, I think I might add the inverse norm and inverse t and add it to that. Next one, and we haven't learned all this stuff yet, but our hypothesis testing, this is also going to help you. And I'm going to get rid of this because I don't like it, but this also will help you for the final review. So it kind of breaks down. Here's for populations, and here's for means, and here's all of the formulas and what you're looking for. So this is going to be really useful. I know that my in-person class, I handed them all printouts of this, and that was like all the notes that they used, and it went pretty well. So I haven't taught an in-person class though since before the pandemic. I miss it, like winter right before the pandemic. Not for college anyway. I really kind of miss them. They keep asking me, hey, you want to be back in person? And I say, yeah. And then the next term, I'm not back in person again. So I don't know what the deal is, but whatever. Woo. I will put in, yes, I will put inverse norm and inverse t on there. Yes. Okay. I'm going to quit the recording. Any questions though about the PowerPoints we just went for before I quit recording? Just on the PowerPoints in today's lesson before we get into homework stuff? Okay. I'm going to stop the recording.